Okay, so let's wait for 1 more minutes if something maybe join. Okay, so hello everyone, I am Subrata Samanta and I am from IIT Kanpur. So I am here one of the TA for the thermal physics course that is taken by Professor Demallo Banerjee in this semester at NPTEL. So in today's session, I will solve assignment 7 problems according to the schedule. So before that, if you have any questions, you can ask now. Okay, so any doubts from the previous week assignments, okay, or from the week contents, okay, so don't hesitate to ask any questions. So yeah, if you have any questions, you can ask now. Okay, so let me share my screen first. Yeah, so hope my screen is visible now, right? Yeah, so hope my screen is visible now, right? Okay, so today we solve assignment 7 problems. Okay, so it seems like there is no more questions. So then I will start the sessions by solving this assignment 7 problems one by one. Okay, so in the first problem, yeah, so in the first problem, so the problem number 1, so 1 gram of moles, I hope it is visible now, right? Okay, so 1 gram mole of perfect gas. So perfect gas means the ideal gas. Okay, so just to note down the perfect gas. So that means PV equals to RT. Okay, so this is the equations of state for a perfect gas. Okay, so this is basically ideal gas. Okay, so ideal gas and expand isothermally. So the second step is isothermally. So that means temperature is constant, right? So isothermal process means the temperature T equals to constant, dT equals to 0, right? So this is constant, so that means that the change in temperature dT equals to 0, right, for an isothermal process. Okay, and yeah, so 1 gram of mole, so N equals to 1, so that's why I wrote PV equals to RT, in general in RT, so here N equals to 1. Okay, so that's why PV equals to RT, the equations of state, right? And isothermally expand 4 times to its initial volume at 27 degrees centigrade. Okay, so that means let's say initial volume V1 or V naught equals to V, and V1 equals to, let's say, 4V, 4 times, right? So according to the problem, this is 4V. So this is V naught to V1 at 27 degrees centigrade. So isothermal process, so that means the temperature is constant. So T is 27 degrees centigrade, so that means 300 Kelvin, right? Calculate the quantity of heat which is extracted for this work, right? So calculate, the next step is to calculate the quantity of heat which is extracted for this work. Okay, so how to calculate the quantity of it, right? So you know that the first law of thermodynamics, right? So the first law of thermodynamics. So what is the first law of thermodynamics? So it's basically the change in internal energy, right? Let's say delta U is delta Q plus delta W, right? Okay. So this is the heat supplied to the systems, okay, and this is the work done by the systems, okay, delta W. Okay. So in this case, for any isothermal, so this is the process is the isothermal process. Okay. So for isothermal process, since the isothermal process, the temperature T equals to constant. So if T equals to constant, right, this implies that dt equals to 0, and we know that the du or delta U is basically Cv times delta T. So this is exactly 0, right? So for isothermal process, the change in internal energy also 0, delta U equals to 0, right? So that means del Q, the calculate the quantity of it, delta Q is basically minus of delta W, right? Now how to calculate delta W for an isothermal process, right? So, okay, so let's discuss in details. Yes, so for an isothermal process, so the equations of state for perfect gas, PV equals to RT 1 mole, right? So where N equals to 1, and the work done W is basically integral of P dV, right? So this is basically now P is basically RT over V, okay, and the limit is V0 to V1 and dV, right? So this is basically RT where the temperature is constant, okay, so this does not depend on the volume. So this is basically dV over V or V0 to V1, right? So therefore the W equals to RT ln V1 over V0. So this is a log, okay, so ln, right? So ln V1 over V0, this is RT times this, right? So this is basically your minus PdV, okay, and according to the sign, so because since dV is negative, okay, so dW is positive, so okay. So this is minus and this is minus. If we choose a sign convention, then the Q equals to minus, so delta Q equals to minus delta W, okay. So this implies that Q equals to RT ln V1 over V0, right? So now in the problem, so this is your formula, right? So now in the problem, V1 equals to 4V and V0 equals to V, right? So if we plug this value, your Q equals to RT. So what is the values of R? Is 8.314, right? Joule per mole per Kelvin, right? So this is the values of R, and what is the values of T? So you have to calculate at 27 degrees centigrade, right? So go back to the problem. So yeah, so the at 27 degrees centigrade, so isothermal process at 27 degrees centigrade, okay, the volume is 4 times, calculate the heat, okay. So then the Q is basically, so T is 300 Kelvin, so Q RT, so 8.314 times 300 times ln 4 over 4V over V, so VV cancel, so it's ln 4, right? So this is basically ln 4, So if you calculate this, so this is basically joule per mole per Kelvin. So ultimate answer is joule. So I transfer to kilojoule. So this is basically 3 point, okay, 46 kilojoule. Okay, okay. So check this answer. So let's go back to the problem and so 3.46. Yeah, so the option C is correct. Okay, so option C is correct. So for any questions, any doubts? Okay, so if not, you can also write in the chat box. Okay, if you have any question. Okay, so if not, then I move to the next one. So in the next question, for silver, the molar specific heat at constant pressure in the range 50 Kelvin to 100 Kelvin is given by this, right? Where T is the absolute temperature. So if 2 mole of silver is heated from 50 Kelvin to 100 Kelvin, calculate the heat required in this process. Okay, so in this problem we have to also calculate the heat, required heat. Okay, but in this case the temperature at constant pressure. So first pressure P equals to constant, right? So constant pressure, and the temperature changes 50 Kelvin to 100 Kelvin. So T1 is 50 Kelvin, T2 is 100 Kelvin, right? And the specific heat, the molar specific heat is given. So molar specific heat Cp at constant pressure, because pressure is a constant in the problem, right? So at constant pressure Cp, so that's why the molar specific heat at constant pressures, okay, we'll denote that as Cp, okay, denoted as Cp. So this 0.076 T minus 0.00026 T square minus 0.15 calorie per Kelvin, right? So let's first copy this. This is the data, right? And T is the absolute temperatures. If 2 mole of silver is heated from, so 2 mole, okay, so N equals to 2 also. So N equals to 2 number of mole, and yes, heated from 50 Kelvin to 100 Kelvin. So again the same temperatures, calculate the heat. So these are the data given in the problem. Okay, you have to calculate the required heat using this data. So problem number 2. So data is given this. Yeah, so now how to calculate this, how to calculate the required heat. So you know that this dq, okay, is basically in the number of moles Cp dt, right? So this is your the concept of specific heat or the heat capacity. So what is the heat capacity? So just quick recap. So the heat capacity, what is the heat capacity? So if you ask the question that how much heat needs to be supplied to an object to raise its temperature by a small amount dt. Okay, so let's write it clearly. So how much heat needs to be supplied to an object to raise its temperature okay, by a small amount, let's say dt, right? So how much heat needs to raise the temperature dt? That is the concept of heat capacity. Okay, so basically dq is proportional to dt. Okay, the proportionality constant, I mean this is not a constant, also temperature dependent, so this is basically dq is c times dt. Okay, so this c is the heat capacity. Okay, so this c is the heat capacity. So for n mole of gas, so this is the formula is that dq is n times c, let's say constant pressure. Okay, so this is your total heat capacity, specific heat capacity. Okay, so this cp and is n times cp, so for n mole gas. Okay, so this is the formula. Okay, so from this, if you just know that what is the molar heat capacity, and the heat capacity per so heat capacity of an 1 mole of substance, the molar heat capacity. So this cp is basically the molar heat capacity, right? So if you go back to the problem, yeah, so the molar specific heat, right, or the molar heat capacity. So the molar heat capacity cp, so this cp is the molar heat capacity. So the molar heat capacity basically the heat capacity of an 1 mole of substance. So the molar heat capacity or the specific heat, okay, of an 1 mole of substance, of an 1 mole of substance. Okay. And what is the specific heat capacity? The heat capacity per unit mass. Okay, the specific heat capacity is the heat capacity per unit mass, okay, or m, right? Okay, so this is your specific heat capacity, and the molar heat capacity is the difference. So in the problem, the molar specific heat capacity is given. So this is the cp, okay, molar specific heat cp is given, and the heat required, so heat required is dq is basically the integral of n cp dt, right? For the temperature is T1 to T2, or the T1 T2 is given 50 Kelvin to 100 Kelvin, right? So now you plug this value, so n is 2, the number of moles, times 50 to 100, right? What is the cp? Cp is given here, is a temperature dependent, so 0.076 T minus 0.00026 T square minus 0.15 times dt. So after integrating this, so we get the 2 times, right? So this is a very simple integral, so 0.076 times t square, so this is basically 100 square minus 50 square over 2, right, minus 0.00026 times t cube 100 cube minus 50 cube over 3, right, minus 0.15 times 100 minus 50, right. Okay, so this is a definite integral. So now after solving this, we will get 403.3 calorie. Okay, just use your calculator and cross check these results. Okay, so 403.3 calorie. Okay, so let's look into the options. Okay, so 403.3, yeah, so the option B is correct, right. Okay, so if you have any questions, you can ask. Okay, or any doubts. Okay. Yeah, I am coming in 2 minutes. Okay, so far any questions? Okay, so far any question? Okay, so then I will move to the next questions. You can also write in the chat. Okay, if you have any questions. So in the problem number 3, yeah, so then the option B is correct in problem 2, right? So in problem number 3, is then an ideal gas of volume 1 liter, right? So but first of all, ideal gas, so we know that the equations of state is PV equals to RT for an 1 mole of ideal gas, so where N equals to 1, and volume 1 liter and at pressure 1 atm, right? So let's say V1 is 1 L 1 liter, okay, and P1 is 8 atm, undergoes an adiabatic expansion. This is important. Okay, so undergoes an adiabatic expansion. So adiabatic expansions, what is the process for the adiabatic process? What is the equations? It's P v to the power gamma equals to constant, right? So this is the adiabatic process. So this is the adiabatic process. Okay, so for adiabatic process, P v to the power gamma equals to constant until the pressure drop to 1 atm. So P1 is 8 atm and P2 is 1 atm. Assuming that Cp by Cv is equals to gamma, okay, so that is given is 1.5, so gamma value is given. So the gamma is 1.5, that is given for an adiabatic process. Calculate the work done in joules during the expansions. Okay, so in this case you have to calculate the work done, okay, in joule. So they also mention the unit joule, okay, where if you see that the pressure is given in atm and the volume is given in liter, right? So first of all, so you have to calculate the V2, right? Since the V1 is given 1 liter, okay, and P1 is given 8 atm, okay, and they undergoes an adiabatic expansions, so that means P V to the power gamma equals to constant, okay, where the P2 is 1 atms, the pressure drop to 1 atm. Have to, but we do not know what is the V2, right? At 1 atm pressure, what is the volume at 1 atm pressure? So we know the volume 1 liter at 8 atm pressure. So you have to calculate first what is the volume at 1 atm pressures. Okay, when the ideal gas undergoes an adiabatic expansions, right? The gamma is given. So the adiabatic process where the gamma is also given. So this is basically the ratio of Cp by Cv. Okay, the heat capacity at constant pressure and at constant volume. Okay, Cp by Cv. So that is given. Okay, so you can easily calculate V2. Okay, so how to calculate this? So let's first copy these informations. So, okay, so problem number 3. Yes, so now I have to calculate V2. So here I have to calculate V2. So that means they follow the adiabatic expansion. So P1 V1 to the power gamma equals to P2 V2 to the power gamma, right? So at the point where the pressure is P1 and V1, okay, they must satisfy the adiabatic equations. So P1 V1 to the power gamma. This is also same when the pressure is P2 and V2, okay, because this is constant. Okay, so this curve, okay, if you draw this PV plane, the PV to the power gamma equals to constant. Okay, so at this point the values of the constant, at this point the values of the constant are same, so that's why these two are equals. So in using these equations we can easily calculate that V2 equals to P1 over P2 to the so over to the power 1 over gamma times V1. Okay, is that clear? So P1 over P2 to the power 1 over gamma times V1, where the gamma is given 1.5, so that means 3 by 2, okay, and P1 is 1 atm and P2, sorry, P1 is 8 atm and P2 is 1 atm, right? So that means V2 is, so this is the ratio, okay, it's a dimensionless, so this is basically 1 liter, so V1 1 liter, so that means 8 to the power 2 by 3 times 1 liter. So 8 we can write 2 to the power cube and then 2 over 3 times 1 liter. So this is basically 2 square times 1 liter, so it's 4 liter, right? So calculate first. Okay, so this is a 4 liter. Okay, okay, any doubts so far? Okay, so this is a 4 liter, right? So now we can know what is the V2. So I have to calculate work done, right? For an adiabatic process, how to calculate the work done? So again, this is basically delta W. Okay, it changes, or dW is, you know, the minus PdV, right? Okay, but the follow the process, this p v to the power gamma equals to constant, right? So once you integrate this, so p basically 1 over v to the power gamma, so this is basically your p1 v1 minus p2 v2 when the pressure is p1 and the volume is v1, to pressure p2 v2 divided by gamma minus 1. Okay, so that is the work done for it. So this is basically delta w, okay, or the w, or you can write delta w, the change. Okay. So using these equations and p v to the power gamma equals to constants, okay, and you can also use the ideal gas law, okay, pv equals to RT. Okay. So it is straightforward to calculate the delta w, okay, for an adiabatic process. So this is a process, so this one is a process, okay, and this is an equations of state. Okay, so this is two different things. Okay. So this is a process, okay, adiabatic process, okay, and this is this one is the equations of state. So if you provided that which process and which equations of states, okay, you can calculate the work done for this gas. Yeah, so now you know, so we know the P1 V1 and P2 V2, we just calculate V2. Okay, so just plug these values here, we calculate the delta W. So the delta W is basically then P2. So what is your P1? P1 is 8 atm times V1 is 1 liter minus P2 is 1 atm times V2 is 4 liter divided by gamma minus 1. So it's 3 by 2 minus 1. Sorry, 3 by 2. Yeah, 3 by 2. So 3 by 2 minus 1. Now the unit is basically, so let's take the unit. So this is basically pressure times, so gamma is a unitless, right? So denominator there is no unit. So the numerator is basically liter atm. That is the unit, right? So volume is the liter and the pressure is the atm in the atm, right? So this is basically 4 over 3 by 2 is half. Okay, so this 8 liter times atm, right? But in the given problem, you have to calculate. So let's go back to the problem. Yeah, so you have to calculate the work done in the joule, right? So you have to calculate the work done in the joule during the expansions. Okay? So during the adiabatic expansions, you have to calculate the work done in joule. But we calculate the work done. We calculated the work done in liter atm units. Okay? How to convert it into joule? So you have to convert it into joule, right? Okay. So again, joule is basically the unit of work done, right? So we know that the work done is basically a force times dx, right? F dx. So the dimension is basically joule and the force is Newton meter, right? So Newton meter basically joule, okay, J. So we have to convert it liter times atm into Newton meter, right? So okay, so 1 liter equals to 10 to the power minus 3 meter cube, right? So meter is basically the distance m, okay, so m cube volume, okay, so it's 10 to the power minus 3 and 1 atm equals to 1.013 pascal, right? So you know 1 pascal equals to, sorry, so 1.013 times 10 to the power 5 Newton per meter square, right? So 1 pascal equals 10 to the power 5 Newton per meter square, right? So now 1 atm liter atm equals to 1.013 times 10 to the power 5 times 10 to the power minus 3 Newton meter, right? So that is basically 1.1.3, so 101.3 joule, right? So therefore your work done delta W is 8 times 1.101.3 joule. Okay, so basically J joule, so it's 810.6 joule. So this is the answers. So 810.6 joule. It's clear? Yeah, so don't hesitate to ask any questions. So using this, that the dw equals to F times dx, we know that the force times displacement equals to work done. So this is basically tells you that the joule is nothing but the Newton meter. Okay, so Newton is the unit of force. Okay, and dx is basically meter in SI units. Okay, so this is in SI units. Okay. And this is basically the work done, the units is joule. Okay. And yeah, so from now I have to convert it liter ATM into joule. Okay, so or Newton meters. Okay. So basically I know that the liter is 10 to the power minus 3 meter cube volume. Okay, and ATM first convert into Pascal and then Newton per meter square. Okay, so this gives simply this. Now let's check the answers. Okay, so 810.6 joule. Check the options in the problem. So problem number 3. Yeah, so first option. So 810.6. So option A is correct. Okay. So now the fourth problem. So yeah, so far any question? Okay, so it seems there is no more questions, so I'll move to the next questions. Okay. Next problem. So it's the problem number 4, right? So a gram mole of helium, okay, so a gram mole, okay, so 1 mole of helium at 20 degrees centigrade is suddenly subjected to a pressure 10 times of its initial value. So pressure suddenly 10 times increases, right? So let's say P1 is HP and P2 increases 10 times P. Okay, so initial value, let's say P, okay, at suddenly changes at temperature T is 20 degrees centigrade. So this basically 293 Kelvin. Okay, so at this temperature pressure changes P to 10. Find the final temperatures, okay, momentarily attained. Okay, so the ratio of the specific heat is given. So the gamma value is given, Cp over Cv is 1.67, right? So now they are not mentioning any process, right? But the gamma value is given, but they are not mentioning which process they follow. So if you carefully read the problem or the questions, is that a gram mole of the helium is suddenly changes. So any sudden change process is basically the adiabatic first process. Okay, so consider as an adiabatic process. Okay, so sudden change process, that means the adiabatic process is PV to the power gamma equals to constant. Okay, constant. Okay, so this is adiabatic process. The gamma value is given, where gamma value is given 1.67. But in this problem, the pressure it changes P1 to P2. Okay, you have to calculate the temperatures. So that means So here is basically, so if we wrote these equations, okay, so here P and V, okay, so first we converted P and T, right? How P and T dependence through this process, okay, adiabatic process, not P and V, because you have to calculate temperature, not the volume, right? So in the previous problem we have to calculate the volume V2, so that's why we use this P V to the power gamma equals to constant, this form, but in this case we have to use another form, right? Because you have to calculate the temperature, not the volume. So okay, let's go back to this. This is the problem number 4. Okay, so the adiabatic process, so basically P V to the power gamma equals to constant, right? But you know the equations of state, so equations of state is always, I mean, provided, sorry. So the equations of state we have to use PV equals to RT, the ideal gas, okay, for 1 mole again. So PV equals to RT, so where N equals to 1, okay. So if we use this, so you can easily convert it that P V to the power, so V is basically RT over P to the power gamma equals to constant, right? So this implies that T to the power gamma, since R equals to constant, okay, the universal constant, so this T to the power gamma, so let's say this constant is C, I have converted that T to the power gamma P to the power 1 minus gamma, it's the another constant C prime, okay, where the C prime is basically C over R to the power gamma, okay. So since R equals to constant, so this is another constant, right? So C prime is another constant because R equals to constant, sorry. So R to the power gamma is also a constant, and C over R to the power gamma, okay, is also a constant. So C prime is a new constant, okay. So this C prime is a new constant, okay, and that is basically follow this, okay. So T to the power gamma P to the power 1 minus gamma equals to constants. So now I have to write the same as before, so that the T1 gamma P1 1 minus gamma equals to T2 gamma P2 1 minus gamma, right? Okay. So in the given problem, what is P1 is P and P2 is 10 times P, right? And what is your T1? It's 293 Kelvin. You have to calculate T2, right? So therefore T2 equals to P2, sorry, P1 over P2 1 minus gamma over gamma, right, times T1, okay. So you can change this, that since that gamma is 1.67, right, so 1 minus gamma is negative, so I change this P2 over P1, sorry, yeah, so P2 over P1 is gamma minus 1 over gamma. Can I do that? It's basically I invert this, okay. So that gives a extra minus sign, sorry, that's why I switch 1 minus gamma to gamma minus 1, right? So you can do that times T1. So now what is the gamma minus 1? This is 0.67. So therefore T2 is P2 is 10 and P1 is 1. So this is 10 to the power 0.67 over 1.67 times 293 Kelvin. So we calculate this. So this is basically 738.01 Kelvin. Right. So 738.01 Kelvin. Yeah. So far any doubt? Okay. So let's check the options. Okay. So 738. Okay. So the option in degree centigrades. So you have to convert it Kelvin to degree centigrade. This is nothing but we have to subtract 273, right? So 738.01 minus 273 degrees centigrade. Okay. This becomes 465.01 degrees centigrade. So 465. Okay, so now check the options. 465.01. Yes, so the closest one is this. Okay, so the option D, 465. Right? So the option D is correct. Right? Yeah, any questions? You can also write in the chat if you have. Okay, so if not, then I will move to the next one. So in the next problem is that yes, so the problem number 5. So for an adiabatic expansions of an ideal gas, okay, the value of delta P by P is equals to, okay, so first you note down the adiabatic expansion. Okay, so the adiabatic expansion is that P v to the power gamma equals to constant, right? So I have to calculate delta P. So that means you have to differentiate this. Okay? So differentiating these equations, okay, is that dP v to the power gamma plus P times gamma v to the power gamma minus 1 dV, right, equals to 0. So that means dP v to the power gamma equals to minus P gamma v to the power gamma minus 1 dV. So this is basically dP over P equals to minus gamma v to the power gamma minus 1 over v to the power gamma dV, right? So this is basically minus gamma dV over V, right? Okay, it's clear, right? So this is dP, and so you have to calculate delta P. So just converted this. So dP over dV minus gamma. So the option B, right? So minus gamma del V over V. So the option B is correct, right? Yeah. Any question? Okay, so it seems there is no question. So this problem is very easy. We just derivative this. Okay, so once derivative, we can get dp. Okay, so first look into that how to get dp, get delta p, right? So by derivative this, and the adiabatic expansion is already given. So okay, so then I'll move to the next questions. Okay, so the problem number 6. Okay, so this is again the statement problem. Okay, so in a cyclic process, the change in internal energy of a system over one complete cycle is, yeah, so this is very important. If you know the answers, you can just mark the options. Okay. So cyclic process, that means the periodic, right? So if you start this point, okay, let's say one process, it's not necessarily circle. Okay, so choose any path. Okay, and then come back to this. So then come back to this. Okay. Right. So now the internal energy is basically delta U, right? So change in internal energy is du. So change in internal energy is du is a function of state, right? So it's basically an exact differentials. So this is an exact differential. Okay, so if time permits, I will discuss more on this. Okay, so what is mean the exact differentials? So this is an exact differentials. Okay, so that means it does not depends on the path. Okay, it only depends on the point. So if you start from this point, okay, and we end up with this point, so there means no change in the initial and final points. Okay, so that means the change in internal energy in this case is 0. Okay, since any cyclic process is basically a periodic process, so that means you have to start from this point and end up with again this point. Okay, so this kind of periodic process. Okay. So your initial points and final points are same. Okay. Okay. It does not depends on the path. So if you choose some other path, okay, it's also same. Okay, or you can, let's say this path, okay, also same. Okay. It does not depends on the path. Okay. So initial points and the final points are same. Then the change in internal energy is 0 because the internal energy is an exact differential. So in this case again the cyclic process. Okay, that means is a point where you start and where you end is the same. This is basically 0. The option A is correct. Okay, so any doubts? Okay, so no doubts, no questions. Fine. Okay, so then I move to the next question. Okay. So problem number 7. Calculate the work done by 1 mole of gas. So here is the work done by the gas. Okay. During and quasi-static isothermal process. So it's treated as an isothermal process. So you know isothermal process means that. So isothermal process. So that means the temperature T is constant. Okay, and dt is 0. Okay, change in temperature 0. The expression of volume 3 V naught to 11 V naught. So here V1 is 3 V naught and V2 is 11 V naught. Okay, here they do not follow the ideal gas equations of state. So the equations of states is given. Okay, so the equations of state is given. So what is the equations of state? P times V minus V naught slightly changed equals to RT. So that is the equations of state. It's not exactly ideal gas equations of state, right? So ideal gas is P V equals to RT. So here is a volume corrections V minus V naught. Right? Then you have to calculate the work done. Right? And the process is isothermal. So again, the equations of state is given. So equations of state is given. Isothermal process is also stated in the problem. So you have to calculate the work done. So again, the same procedure for the volume changes V1 to V0, V1 to V2 at constant temperature. So I have to calculate the work done for an isothermal process. So problem number 7. So okay, so isothermal process, how to calculate work done. So what is the delta W? So for an isothermal process, temperature is constant. That means dt equals to 0, right? So that means du equals to 0 is basically Cv dt. Okay, is 0. Now what is the dq? Then dq according to the first law is minus dw, right? So this is basically your dw is minus pdv, right? So that is we know. Now I have to integrate. So you have a equations of state. So what is the equations of state? Is P times V minus V naught equals to RT. So replace this instead of P. So what is that? So basically this is one is that so W, this is the dW. So W equals to minus, right, V1 to V2, and P is basically RT over V minus V naught, and then dV. So this is minus RT ln V2 minus V naught over V1 minus V naught, right? So what is the V2 is 11 V naught, and what is the V1 is 3 V naught, the given problem, right? So in this case, if you see that the V1 to V2 is increases, right? So that means dV is V2 minus V1 is basically greater than 0, right? So that means there is a no minus sign. That means, so since the volume the V1 to V2, that means the gas work done by the gas, not work done on the gas. Okay, so volume is expanded. Okay, so that means there is a plus sign, no minus signs. Okay, so this sign is crucial. So the minus signs we written in convention since that if the gas is compressed, okay, so work done on the gas. Okay, so that means the pressure increases, right, and the volume decreases. In that analogy, the work done is positives, okay, because the dV is negatives. Now in this case, dV is positives, okay, so there is no need to put a minus sign extra, okay, in the front of this. Okay, so this is a plus sign, okay, and this is also a plus sign. So then the RT ln, now this V2 is basically 10 over 2. This is RT ln 5, right? So RT ln 5. Okay. So what is the values of R? 8.314 times what is the values of T? Is it isothermal expansion? So what is the values of T? Yes, so T is 27 degrees centigrade, right? So that means 300 Kelvin. So T is 300 Kelvin. So times 300 times ln 5. So this is basically in joule, right? So it's 4012 joule. So this is the answers. Okay, so let's check the options. 4012 joule. Yeah, first of all, so far any questions. Okay, so that is important. So if you have any doubts or questions, then I will match the answers. Okay, otherwise, yeah. So if you have any doubts, then first clear this. Okay, so no doubts, right? Okay, so now let's check the answers. Okay, so 4012 joule. Option is 401. Yeah, so the option C, right? The option C is correct. Okay. Okay, so now go back to the problem 8. So the problem 8. So an ideal monatomic gas and a diatomic gas is adiabatically expanded from pressure volume Pi Vi to PA Vf. Find out the ratio of work done for the monatomic gas and the diatomic gas. Yes. So the process is important. Okay. So the adiabatic expanded. So you know what is the adiabatic process and what is the work done for this process. The monatomic gas and diatomic gas, I will come into this point later. So for an adiabatic process, that means PV to the power gamma equals to constant. Right? Where the gamma is the adiabatic index, right? So this is the adiabatic process. Right? So now for the monatomic gas and the diatomic gas, the gamma value changes, right? So for monatomic gas, okay, so your gamma is basically 3 by, how to calculate this? This is very interesting. So for monatomic gas, how to calculate this? So what is the degree of freedom for monatomic gas? What is the degree of freedom? F. F is the number of degree of freedom. For monatomic gas, the number of degree of freedom only translation motion, right? So it's 3, right? Then the gamma is basically the ratio of Cp by Cv is 1 plus 2 by F. I think I will derive. I have derived this. Okay, at some point. Okay, maybe in the first class. Okay, go back to this class. Okay. This recorded lectures. Okay. So now if you put F equals to 3, so this is basically 1 plus 2 by 3 is 5 by 3, right? So this is the value of gamma for monatomic gas. Similarly, we can calculate for diatomic gas. So for diatomic gas, So for diatomic gas, what is the values of gamma? What is the value, number of degree of freedom? F. It's 5, right? So 3 translation, 2 rotations. It's important. So this is basically this. Okay. So 3 translation plus 2 rotation. Right. So total 5 degree of freedom. So then the gamma is 1 plus 2 by f. So it's 1 plus 2 by 5 is 7 over 5. Okay. So 1 plus 2 by 2 over 5, so it's 7 over 5, right? Okay. So it's clear or not? Okay. So now we know that the gamma mono, so let's say for monoatomic gas, it's 5 by 3 gamma diatomic gas for 7 over 5. Okay. And you know the work done for an adiabatic process. So what is the work done for an adiabatic process? So for Pi, Pi to PF, PF, okay. The pressure is changes, Pi, Vi to PF, PF. Okay. What is the work done delta W? They follow a adiabatic process. We just calculated this, right? So yeah, this one. So P1 P1 to P2 P2 by over gamma minus 1. So this is basically delta W is P1 sorry Pi Vi minus PF VF over gamma minus 1, right? So the delta W for monatomic gas, right, divided by delta W for diatomic gas. Okay, so the Pi Vi and PF VF are same, so only changes is the gamma. So gamma diatomic gas minus 1 over gamma mono minus 1, right? So then this is 7 over 5 minus 1 over 5 over 3 minus 1, right? This is basically 2 over 5 over 2 over 3, 3 over 5, right? So 0.6, right? Any doubts? So the work done for different gas, monatomic, diatomic gas, okay, it changes because the gamma changes. For the monatomic gas, the values of gamma, and for the diatomic gas, the values of gamma is not same. Right? The initial Pi, Va, and PF were same for both gases, okay, and the process is also same adiabatic process, but the gamma is changes, okay. So that's why the work done it changes, okay, and I have to calculate the ratio of this. So this that is basically gives 0.6. Okay? So it's simple, quite. Yeah, it's quite simple. Yeah. So if you have any questions. Okay, so it seems there is no more questions. Okay, so let's check the options. Okay, 0.6. Yeah, so the option B. Okay, so option B is correct. Okay, so how many problems are left? 2. Okay. So yeah, so if you have any questions. Okay, so then I'll move to the problem 9. So the temperature of 1 mole of gas is raised to 100 degrees centigrade from 20 degrees centigrade, right? So again, first of all, note down this 1 mole of gas, and the temperature T1 is 20 degrees centigrade to 100 degrees centigrade, right? So converted to Kelvin, 293 Kelvin, 373 Kelvin, right? So what is the difference between this T2 minus T1? 80 Kelvin, right? And the values of R, this is the universal constant, 8.314 joule per mole per Kelvin. Okay. Now the process is the polytropic process, not the adiabatic process or the isothermal process, the polytropic process with n equals to 1.4. Okay, so this n is different. So so 1 mole of gas is the number of mole, right? So that is n, but the here is the n is the polytropic process. So the what is the polytropic process? The polytropic process is p v to the power n equals to constant. So this n is an arbitrary number, okay? So here n is the free parameter, okay, not the adiabatic index gamma. Okay, so if it is gamma adiabatic index, that is basically gamma is basically the specific quantity, that is Cp over Cv, Cp over Cv, right? But here n is the arbitrary number, okay, that is not some ratio of specific heats or something else, right? So that's why this is a adiabatic process, okay? So if gamma p v to the power gamma equals to constant, this is an adiabatic process, okay? So that means if n equals to gamma, this is an adiabatic. If n equals to 1, this is an isothermal, okay? And for other values of it, this in general is a polytropic process. So in the problem, the n value is given 1.4, right? The values of n is given 1.4. Okay? So this is some kind of polytropic process where the n is 1.4, okay? Not the adiabatic or not the isothermal. So in that process, we calculate the work done. Yeah, so how to calculate? So again, the same procedures, right? So we know that the dW equals to PdV, and the equations, the process. So the equation is basically ideal gas equations, right? So P process is P v to the power n equals to constant, where n equals to 1.4, right? And the equations of state is PV equals to R. So these two informations are needed, okay? Which equations of states you are using and what is the process. So then the dW is minus PdV, okay? And you just calculate this because we have calculated for adiabatic process PV to the power gamma equals to constant, okay? So for this case, we calculate the work done delta W is Pi Vi minus Pf Vf, okay, over gamma minus 1, right? So same case, okay, because the process almost, I mean, the Pp to the power gamma, the form is same, right? So now Pv to the power n is constant, right? So that's why we replace gamma by n in this calculation, right? So here only need the form of the process, okay? So this, in this case, then again the delta W is basically Pi Vi minus Pf Vf over n minus 1. Okay, this is the work done, okay, for polytropic process, right? So now for they follow these equations of states, okay, ideal gas equations of states. So that means Pi Vi is basically RTI and Pf Vf is basically RTF, right? Right. So plug this value. So the delta W is R over n minus 1 times Ti minus Tf, right? So now in the given problem, what is the Ti minus Tf? So if you look into this, so yeah, so here T1 is the, yes, so T1 is the 293 Kelvin, sorry, T1 from 20 degrees centigrade, raise the temperature is raises and calculate the pressure is fixed, so keeping the P is constant, so P is constant, okay, and temperature is changes, so it's basically 20 to 100, so that means there is a negative sign, right? So T2 minus T1 80 Kelvin, so T1 minus T2 is minus 80 Kelvin, right? So that means R value is 8.314 and the values of N is 1.4 minus 1 times minus 80, right? This is joule, so it is equals to minus 1662 joule, 1662 joule. So there is a minus sign, okay, so that is important because Ti initial temperature is 20 degrees centigrade, okay, and the final temperature is 100 degrees centigrade, right? So temperature is at pressure constant, okay, temperature increases, right? So at constant pressures, if the temperature increase means, what is the equation of state? PV equals to RT. If pressure is constant, then the volume is proportional to temperature, right? Okay, so if pressure is constant, then the volume is proportional to temperature, right? So that means the temperature increases, that means the volume increases, right? Okay. So that means work done by the gas, not work done on the gas. Okay, that's why the negative sign here indicates this. So find out the work done. So work done is negatives and minus, so 1662 joule. Okay. So at fixed pressures, if you raise the temperature, so that is work done on the gas and the work done is negative. So okay. So this negative sign is clear, right? Because initially we have choose that there is a, if the dB is positive, then I choose the plus signs. Okay, I could, so in the derivations there is a nowhere I use the negative signs, but at the end I get the negative signs. So that is the things you have to keep in mind. So now the problem number 10. Okay, yeah, so far any questions or any doubts? Okay, so if not, then I will move to the last one, or the last problem. So okay, for an equations of states of an ideal elastic substance. Okay, this is not a gas. Okay, it's ideal elastic substance. Okay. And the equations of state is given F equals to some constant K times T. Okay, so K is some constant. Okay, and F is the tension. Okay, and L is the length. Okay, so and L0 is the length at 0 tension. Okay, where F equals to 0, and is a function of temperatures. Okay, the length is a L0 is a function of temperatures. Okay, only find the expressions of the work done required to change L from L0 to 1 over 3 L0. So if we change the length from L0, so from L0 to 1 over 3 L0, so your initial length is L naught and the final length is 1/3 L naught. Okay. Similarly, for gaseous systems, you just change the volume V1 to V naught. Okay. So for in this elastic substance, okay, you just changing the length L1 to L2. Okay. And I have to calculate the work done. Again, the process is isothermal. Okay. So the first is that note down the isothermal process. Isothermal process, so that means the temperature T equals to constant. Okay. So this process is same. Okay, whatever your substance, elastics or gaseous, your process is same. For isothermal process, that means the temperature constants. Adiabatic process, that means the so for gaseous systems, we know there is adiabatic process, the pressure volumes. Okay, but in this case, it's not the case. Okay, so in the isothermal case, that means the temperature constants. Okay, because pressure and volume there is no meaning here, right? For ideal elastic substance, okay? So there is no pressure volumes, there is a tension. Okay. Okay, so then you have to calculate this. So this is I think the system just looks like something this. So we have a elastic, let's say, rod, and the tension is it's so this is and the tension is this. Okay, right? Yes. So this is your force. Okay, and this is the length is L. Okay, so this is the tension. Okay, and the F is the tension. It's kT times L over L naught minus L naught square over L square, right? So L is the arbitrary length. Okay, and this is the equations of state. So this is the equations of state. So now to calculate the work done, it's dW, right? It's basically F dx. Okay, so the P dV is just replace F dx. Okay, so P is replaced by force, sorry, tension. Okay, and dV is replaced by dx. So again, you have to change the del W for changing the length L1 to L2. Okay, this is F dx. Okay, sorry, F I think if you so here I use, say, use x. Okay, x square. So yeah, so now if we plug these values, just copy this. Yeah, so this is the equations of state. So now you plug this value. So kT times L1 to L2 x over L dx minus L1 to L2 L naught square over x square dx, right? So after integrating this, so this kT is 1 over L naught L2 square minus L1 square minus so this is a plus, okay, L naught square 1 over L2 cube minus sorry 1 over L2 minus 1 over L1, right? Okay, yeah. So now if L1, so suppose your L1 is greater than L2, so this is true for L2 greater than L1, right? So this is true for L2 greater than L1. Okay. So if L1 is greater than L2, right? So that means L2 is small. Okay, so it's compressed, not elongate. Okay, not elongate. So in that case, so if L1 greater than L2, in this case we have to use W equals to minus L0 to, let's say we're changing the length L0 to L0 over 3 in the given problem, right? So in the given problem it changes the length L0 to L0 over 3, that is if dx. Okay, and we put a minus sign, sorry, extra minus sign, okay, because already saying that changing the length from higher to lower value, okay, so the dx is negative. So, okay, so that means the dw, I mean the w is positive, so that's we put a extra minus sign, okay, in front of this. So this is basically minus kt. Okay, so here is 1 over L0 times L2. L2 is L0 over 3, so 1 over 9 minus 1, right? And this is basically L0 square plus L0 square 1 over L2, so L0 over 3 minus 1 over L0. Okay, so this is becomes minus kt minus 8 sorry 8 over 9 L0 square plus 2 L0, sorry L0 and plus 2 L0, right? So that means minus kt times 10 over 9 L0, right? So L0 to L0 over 3, so 1 over 9 and then is that 14 over 9, just a minute, 18 and 9, sorry there is a 2, right? So sorry I missed this, so there is a 2, so L0 square over 2 L0 over 2, so that means this is basically 9, so this 2 to 4, so 14 over 9, yeah, so the answer is minus 14 over 9 kt L0. Okay, so any questions so far? So when L2 is greater than L1, I have not used any minus sign here, right? So this is true for L2 greater than L1, right? Okay, so I am not using any minus sign in this equation, right? But when if L1 is greater than L2, then I use extra minus sign in front of this, okay, because the work done is negative. Sorry, when the dx is negative, so the work done is positive. And that's negative sign actually indicate this. Okay, so if in doubts or any questions? Okay, so let's check the options. So the minus 14 over 9 kt L0. So yeah, so the option D is correct, right? So minus 14 over 9 kt times L0. So option D is correct. Okay, so this one is the last problem. Yes, so any questions, any doubts, or if you have any question in doubts from this week assignment, so this year assignment, so you can also ask. Okay. I hope you are able to solve this week assignment problems. Okay. So it's very similar of these problems. Okay, just changing the numbers or changing the values. Okay, but the type is almost same. Okay. Okay, so if there is no more questions, then I will discuss some basic concept about the first law of thermodynamics and the related stuff. Okay. So first of all, what is the heat? Okay. What is the definitions of heat? Okay. So what is it? So basically, heat is an energy, okay, in transit. Okay. So heat is energy in transit, right? So that means you can add heat to the system, okay, or to an object, okay, but you cannot say that the object contains certain amount of heat, certain quantity of heat. So you can add heat to the system. So you can add heat to the object, but you cannot say that a object, okay, contains certain amount of heat, contains certain amount of heat, right? Because an object contains certain amount of energy, okay? Because the object contain certain amount of energy, right? Not the heat. Okay, so heat is energy in transit. Okay, you can add heat, but you cannot say that. Okay, the object has certain amount of heat, so certain amount of energy the object have. Okay. So now the heat capacity. The next concept is the heat capacity. This is the heat, okay. And now the heat capacity. So I already told that the heat capacity is basically that the dq. Okay, so the how much heat needs to be supplied to the student systems to raise the temperature dt. So dq is basically c times dt, where c is dq over dt. Okay, so this is the heat capacity. Okay, so now the heat capacity for a gas. Let's say the constant pressure. So what do you mean the heat capacity at constant pressure? So at constant pressure, so that means P equals to constant, right? So when we adding heat, but the pressure increases, right? But you say that so this is true at constant volume. So when we add heat, pressure increases. That means the volume is constant, right? So again, recall the equations of states. PV equals to RT. So if you increase heat, that so if you add heat, right? So that means increase the temperatures. If pressure constants, that means volume increases, or if volume constant, that means pressure increases, right? So if pressure constants, that means volume increases, right? Adding heat. Okay, so recall the equations of states. So this is the equations of states. Now at constant, so this is denoted at Cp. Okay, so this is basically dq over dt at constant pressure. So now at constant volume, so that means adding heat is basically your pressure increases. So again the equations of state is PV equals to RT. Okay, so this is basically CV is dq over dt at constant volume. So recall the equations of states. Okay, that is the important concepts. Okay, so this is since yeah. Okay, so that is the two things I have to discuss, and now I'm going to discuss the functions of state, right? So basically, so the concept is basically energy. Okay. So what happens when an energy changes from one form to another? So I'm asking the questions that what happens or what happens when energy is changed from one form to another. Okay, so one form to another. What happened when the energy changed one form to another? So that is basically tells you if you know the functions of state. So what is the functions of state? Functions of state. So it's basically a system in thermal equilibrium, then all the macroscopic observable properties are fixed. Right. So if a system is in thermal equilibrium, so in thermal equilibrium, okay, so the macroscopic property is fixed. So the macroscopic properties, okay, are fixed, right? So that means pressure, temperature, volume, energy, okay, for gaseous system. So this is for gaseous system. Okay, and the functions of state is a function of state is any physical quantity, okay, that is a well defined value for equilibrium states, okay, for each equilibrium state of the system. So there is a various equilibrium state of the systems, and a functions of state, so a functions of state, okay, is any, so its functions of state is any physical quantity, okay, that has a, so that has a well defined value for each equilibrium state of the system, for each equilibrium state of the system. Okay. So it's independent of how they got there. Okay, so this is basically the important thing is that the independent of how they got there. Okay, means that the equilibrium states, how to reach the equilibrium states. Okay. That's the independent of this process. So if you calculate the mathematically, we can say that the delta f is x1 to x2 df, where the f is the functions of state. Okay, then the changes where f is the functions of state. Okay, so then the delta f is basically the changes from x1 to x2. Okay, and this f is, let's say, functions of some xi. Okay, So x1 to x2 df is basically f of x2 minus f of x1. So only depends on the endpoint. So, okay, x2 at end and x1 does not depend on the path. Okay. So basically, let's say this is the functions of state. Okay, and this is a variable. So I have to reach this point. Okay. So let's say this one is my x1 point and this is the x2. So from this point, I can go this path, right, and then this path. Okay, or I can go this path. Okay. So the two different paths. Okay, so one is that so this is basically, let's say, number 2, and this path is number 1. But that only depends on this x2 minus f1, the endpoints. Okay, does not depend on the path. So this df, so then this df is basically an exact differential. Okay. So if f is not a function of state, then df, okay, so this implies that the df, okay, inexact differential, inexact, okay, so inexact differential, right? So that is the meaning. Yeah, so far any questions? So the answer to the example is that the f of pvt equals to 0. This is, let's say, functions of state. So this basically gives you that pv equals to nkbt. Okay, that is this function of state is basically equations of state. So equations of states, right? Okay, so far any questions? So I'll stop here. Okay, so if you have any questions you can ask, otherwise I'll stop the session here. Okay?